Thank you, Roy. Our next speaker is William Gray. William Gray has worked in the observational and theoretical aspects of tropical meteorology research for more than 40 years. He has specialized in the global aspects of tropical cyclones for his entire professional career. Help me welcome William Gray.
Thank you, Mike. Well, thanks. I'm glad to join this group. That was very complimentary, 40 years. It's over 50. But anyways, I've been hanging around in the field a long time and thinking, and I've been appalled for 20 or 25 years at all I've heard about the global, human-induced global warming. And I think the main thing that's causing climate change is the oceans. But I agree with my colleagues here, sitting up here. I think the ocean changes have led to the PDO changes and the things that they've just showed you. I think we can relate the whole thing. So the theme of this talk is that it has generally been in the field, CO2 inhibits radiation to space, so everyone's been concentrating on radiation. And we need, there's been too much radiation, not enough ocean. Too much radiation, not enough ocean. And I want to put in the ocean here. Now, there's certain cardinal principles we follow. Better to be right in hell, have all your colleagues not speak to you, not be able to get grants, but be right, than to be wrong in heaven and get all your grant money and all those things, but you're living a lie. Anyways, so the summary of this talk is that the GCMs have given much too much global warming, and they shouldn't be taken seriously. I'm going to point out some of the problems in them. And the deep ocean circulation, in my view, is a primary driver, and the models don't handle that, or if they have an ocean circulation in, they don't do it right. Because if they did it right, they wouldn't be getting the warming they are. I'll skip over the politics. I had a lot of politics here. Anyways, we know that the greenhouse gases, there's CO2, of course, and it's a logarithmic effect. So even though if we have the background state, it causes roughly 2 degrees warming of the system. If we double it, it'll go to 1. And if you pick it up more, the increment of it blocking long wave to space becomes less and less. But the main greenhouse gas is water vapor. And that creates a lot of global warming. Now, the GCMs say if you double CO2, you get this amount of warming, but there's a positive feedback. And this is where they make errors of roughly 2 degrees, 3 degrees, something like that. And that's where you get the 2 to 5 degrees warming with a double of CO2. The results I've been looking at many years, and my colleague out here, Barry Schwartz, we're beginning to question this, and we see, if anything, in the middle and upper troposphere, where it's so crucial what the vapor is, the vapor doesn't go up. And this Clausius-Clapeyron equation and the general theory of the models is that the relative humidity remains constant, so as the globe warms, your Q or your vapor goes up. Now that's probably a fair assumption in the low levels and for the net vapor in the column, but in the middle and upper troposphere, it doesn't seem to hold. And that's a crucial difference. So Here's what I'm talking about, this famous Charney report of 79, you know, the Clausius-Clapeyron equation. As the temperature goes up, if the humidity remains constant, then the ability of the air to hold vapor goes up. But when we measure the middle troposphere, my colleague Barry Schwartz sitting out there, we don't necessarily find that. Now, there's a lot of controversy with this, so we're looking very hard at this, and this might be one of the things that go on. If you have more convection and you have more evaporation, the vapor in the lower layers can go up, but if some of that leads to deep cumulonimbus clouds, the more intense the cloud, the higher it goes, and the more mass goes up in the cloud to give more rain, the more the mass subsidence on the side can go, and the actual emission level can actually slightly go down, and you can get more IR loss to space. So that may be one of the explanations for this. We're looking a lot at this. We're looking a lot at the ICCP data, the International Satellite Cloud Climatology Project, but we've got the albedo data. Barry's been working a lot with that, so it's remarkable what the albedo does to look at both of these things. We've got the reanalysis data we have, but people question that and so on, but overall, I think there's some good meaning in that data. And this is sort of what we see. If you look at the whole globe, now you'll criticize the data, but here's a 400 millibar specific humidity, or Q, and it tends to be not going up with time as it should if the globe warms, but rather going slightly down. And looking at the SCAP data, Barry Schwartz worked at, it looks like some of the middle level precipitable water is actually going down, not up. Now I want to turn to the models. What did Jim Hansen in his early models show? This is what he showed. When he doubled CO2, he made his Q values in the upper layers increase by 50% and his relative humidity in the upper troposphere go up. That was his early model he reported on to Congress in 1988 and got everybody worked up and so on. This is, if you look at his upper level temperatures, this is what Hansen got. He got that when you double CO2, you're going to get upper tropospheric warming of 7 degrees C here. This is, if at the emission level, this would mean energy going out at about 23 watts per square meter, something like that, when the forcing itself with a doubling is only about 3.7. So of course Hansen got warming because he assumed there's as the CO2 built up, he put all this extra water vapor in his model. Well, they all do that. They all did this. This is the early models from the Met Service. They look at the warming they have in. They put this upper tropospheric warming. Now, Dave Frederick yesterday talked about this with some of the recent models, and he showed that how the data doesn't agree with the recent model, the changes they've had over recent years that have been warming the upper troposphere a great deal. That's not happening. And I'm just showing these other things. Now, if you go to NCAR, the same thing. Look at this warming, 3 degrees up here in the upper troposphere. GFDL, the same thing. They all do that. And they're all wrong with that because there isn't that much warming. It's the feedback of the water vapor they put in that gives all this warming. And how they've been able to get away with it so long, I don't understand. I remember Lindzen and I had a talk about 15 or 18 years ago at a meeting once, and we both, I was surprised he was a skeptic with global warming, but he was, and we both agreed it's the upper level water vapor. Of course they get what they get because they put so much in there that's not realistic. Also, the observations, the models tend to correlate. The water vapor changes in the lower troposphere correlate with the changes in the upper troposphere, but the obs don't show that. Also, in a relative comparison, if you compare the solar energy in and the IR and albedo out every day with the amount that occurs every day, with the amount of what's happening in the last 100 and some years, you see how small, in a relative sense, the CO2 is compared to the other things. Also here, and every day we have so much condensation in the atmosphere, so much re-evaporation, rainfall, and so on, all these numbers. Every day, this is about 1 million times or more greater than the forcing of this CO2. Have you ever seen a graph like this where the CO2 is prepared from zero? Here, you can see, yes, it is increasing. Yes, between 75 and 08, it did go up about 50 parts per million by volume, giving a energy change of about 0.6 or so, and that would be equivalent to a temperature change of about 0.14, but the real temperature change was 0.5. Something else has been going on. You can't explain the warming just from the CO2. So what is the cause of it? Well, I think it's the deep ocean circulation. We have the thermohalion circulation where Atlantic water goes up here and sinks. We also have sinking around Antarctica, and this water sinks and upwells in tropical South Pacific. And when this circulation goes faster than normal, we tend to have global cooling. When it's warmer than normal, we have global warming. Now, I discount other things. I love Willie's song, but I believe solar and sunspot activities. I believe volcanic activities. I think they do something. Yes, there's something there, but they're not the dominant thing. They can't explain the full temperature. Neither can cosmic rays, aerosols, and these other things. So I think the only thing we have left is the ocean. Other than the CO2 will not do it by itself, and one of the problems we have as critics of CO2 is we don't have a unified physical theory that explains the global temperatures. If we do, we could say, look, this is the way it goes. This has all this evidence for it. CO2 doesn't have as much, and we could sell the day, but we have no unified view the other way. Now, here's what the oceans do. I was glad to see Governor C. Unu talk about the ocean, how they were right on the ball. If they criticized in the early days when he was the assistant to the elder Bush, when they brought in their science experts, they criticized him on the ocean. That was a very good thing because they didn't have the ocean in, and that was the Achilles heel, in my view. So you see, if you have in the North Atlantic here, you have sinking here, you have sinking. These are related. I don't have time to talk about them. When you get more sinking here, in general, on a multi-decadal scale, you tend to get more sinking here, more upwelling and more cooling here. And when it's weaker, you have weaker sinking here, less upwelling, and the globe tends to warm. It's as simple as that. And I don't think I'll take time to explain it. So it's the MOC, we say. The meridional overturning circulation is made up of the Atlantic thermohalion one and the surrounding Antarctica one. This is about twice as strong as that typically. And you might say in Sverdrup units, the average is about 15 Sverdrup units, sinking here about 10, upwelling about 25. But there are periods when this is stronger, and you're upwelling 35 Sverdrup units here, and when it's weaker, you may be upwelling 15 or 20 or so. So that is the driver. Now, what causes these differences in sinking? Salinity differences. Don't have time to talk all about this, but anyways, we have the sinking up here. We have this sinking. We have the sinking on Antarctica, and we have the upwelling in this area here. Sometimes it's stronger than normal. Sometimes it's weaker. It's presently stronger than normal. Since 1995, the North Atlantic thermohalion got stronger, and I don't know about the southern hemisphere, but in time that may change. And given a lag, you always have a lag of 5 or 10 years here for the temperature to respond to the ocean changes. But we've seen it. Apparently, there was warming up to 98, 99. Now we haven't seen much warming, and maybe some slight cooling from 2001 on. So there are times when this is stronger. Now this is related to salinity. There are multi-decadal periods when this Atlantic thermohalion is strong, other periods when it's weak. It relates to hurricanes very well. We get twice as much or more intense hurricane during years when this is strong as when it's weak. This is what got me onto it, was hurricane. What did that say? 2 hours? 2 minutes. Okay. Anyways, I think I'll jump ahead. The Atlantic, like the PDO, the Atlantic goes through these oscillations where this thermohalion stronger, weaker, and so on. And when this happens, when the thermohalion is stronger, we tend to have a globe where we have more rain in West Africa, more hurricanes, more blocking action, more ridging here that is related to the PDO, fewer El Niños here, and the opposite. When this is weaker, we have more El Niños, and the PDO or this trough and ridge pattern that you have a strong ridge off the coast here, stronger westerly winds, and in general less rain, slightly less rain, and that less rain means the surface evaporates less and can warm more. There's less upwelling of cold water, and that's why the globe tends to warm during these situations when the MOC is weak versus when it's strong. I have more facts here. So now I also, one other point I want to make, I see there's multi-decadal variations in this MOC, but there's also multi-century variations. And what I see is in the 20th century, we've had generally the MOC was weaker than it was in the 19th century. And we had this long, generally weak thing that made the global temperatures go up in the 19th century, but superimposed upon that was the multi-decadal variations, and they were up and down, up and down. And my prediction is in 15, 20 years, the globe is going to be slightly cooler than it is now. So we have these multi-decadal variations. I think in the 19th century, things are, the thermohaline was stronger. So if humanity had come along a century sooner and the Industrial Revolution had occurred in 1750 rather than 1850, I think in the 19th century we wouldn't have had the warming that we've had in the 20th century. The warming in the 20th century is essentially a product of a multi-century slowdown in the MOC. In the Little Ice Age, it was faster. In the medieval warm period, it was slower. In the Roman warm period, it was weaker. And these are natural changes driven primarily by the ocean, and the ocean's driven by the salt, and the ocean drives the PDOs up and down in various ways. So, one other thing. So I'm now done, but I've got some, I wrote, if I die on the way home, that's my last will and testament. I've got some papers here, about 100 of them, and another political statement of 6 pages that knocking the American Meteorological Society giving its highest award to Jim Hansen. So if you, after the talk, if some of you want to pick up this, you can pick it up. I want to thank my colleague Barry Swartz, sitting out in the audience there. Raise your hand, Barry. There he is, for a lot of work too. So thank you.